Last time, we spoke about continuous random variables. We spoke about and their associated distributions. We spoke about the normal, the multivariate Gaussian, as well as the gamma distribution. An important point that we brought up was the fact that we can calculate the probability over some domain, let's call it domain eta, as the integral over that domain dr p of r. So this would be the probability of finding the random variable over some domain eta. And we also mentioned the fact that if eta is equal to the whole domain, then the probability of finding the random variable over any region over its entire domain is equal to 1, and that's the condition of normalization. We had integrals because we dealt with continuous probability distributions. But what I'd like to do now is to sort of switch gears a little bit and talk about discrete probability distributions. And we're going to formulate those in two different ways. So, a discrete probability distribution is used to describe things sort of a little bit abstractly, like coin flips, dice rolls, but it could also be used to describe, for example, the number of cells in a cell population. That's also a discrete quantity, right? So 1 E. coli, for example, on a plate becomes 2, 2 become 4, and so on and so forth. So whenever you have sort of a discrete number of things, you typically deal with discrete probability distributions. So one way to write discrete probability distributions is as P of R, and we're going to rewrite P of R as, for example, the probability of getting outcome 1 multiplied by delta function, which I'll describe shortly. This basically is a spike at the value of R, which is equal to rho 1, but we'll talk about it. Then there could be a second outcome, pi of rho 2, delta function sub rho 2 of R, and so on and so forth. So if I were to write this sort of as a sum, I would rewrite this as the sum over m from 1 to big M, pi of rho sub m times delta rho sub m of R. Now, let's talk about those spikes. I've been calling them delta functions. Those spikes have a very specific property. If my R is not equal to rho, in other words, if I try to draw a random variable which is not in the allowed set of outcomes, then my delta function returns a 0. On the other hand, if I were to integrate over all possible values, I should get a 1. So at some point, the R will be equal to rho, and this integral here will be equal to 1. So another way of thinking about this is as if I were to plot the probability versus the outcomes for discrete distributions, and the first outcome could be rho 1, second one rho 2, all the way up to rho big M, then the probability of the first outcome would be pi sub rho 1, and the probability of the second outcome here would be pi sub rho 2, and maybe the probability of the third outcome is, or the mth outcome I should say, maybe even lower, and this one here will be pi sub rho big M. Now, if I do a coin flip, for example, I have some probability of outcome 1, maybe that outcome is heads, and some probability of outcome 2, that outcome is tails, and I know that pi of rho 1 plus pi of rho 2 must be equal to 1, right? Because the probability of heads plus the probability of tails is equal to 1. Similarly, if I were doing a coin flip, I would have pi rho 1 plus all the way up to pi rho 6, a dice roll. I would have pi rho 1 all the way to pi rho 6 equal to 1. So let's verify at this point that my discrete probability distribution, so this is going to be a sum from m is equal to 1 to big M of pi sub rho m delta function rho m of r. This tells me again where the spikes are allowed, where the specific values of r are allowed. So let's verify that if integrated over the entire domain, p of r is truly equal to 1. In other words, that this representation for discrete random variable probability densities is normalized. So this again, we have a name for this, and it's called a normalization condition. Okay, so how are we going to verify this here? So let's go ahead and try doing the integral. So we're going to have the integral dr of this sum. I'm not going to write the boundaries of the sum just to save a bit of time at this point. Rho sub m delta rho sub m of r. Now, the only thing in the integrand here to depend on r is the delta function. So I'm going to move my integral dr past the pi. Now, if we remember what I said last time, at some point r will be equal to rho sub m. When that happens, the delta function here will integrate to 1. And what I'm left with is a sum pi rho sub m. Now, what is the sum equal to? Well, we've already said the probability of heads plus probability of tails needs to be 1. So for any sort of discrete random variable, the probability of each one of the outcomes needs to sum to 1. So this sum here is 1, and therefore we've verified the normalization condition given our formulation for the probability density for a discrete random variable. So let's go ahead and erase this here and talk about the way we would normally write this. So we would say that r is drawn from one of very many categories. And to do that, we talk about the categorical distribution, which I'll talk about a little bit more in a second. And we imagine that there are multiple categories or outcomes. Those are rho 1 all the way to m. And the probability for each one of those categories is pi sub rho m. So if I were to write out this entire thing a little bit more explicitly, for the case of a coin flip with only 2 outcomes, what I mean by this is that I have rho 1 comma rho 2, and the probabilities for those outcomes is pi sub rho 1 and pi rho 2. So this is for the specific example that I have 2 outcomes, or 2 categories more generally, and the above is for m categories. Now, the discrete probability distribution coinciding with 2 categories is very often used, and it actually has a special name. And it's a special case of the categorical distribution, and it's the so-called Bernoulli distribution. So oftentimes for coin flips, we will simply talk about the Bernoulli distribution. And this Bernoulli distribution here has one parameter, and that parameter is referred to as pi. Now we can ask ourselves the question, it appears that the coin flip here has 2 parameters, and if I choose to give it a different name, I've reduced the number of parameters to 1. How's that possible? Well, writing it more generally as a categorical, I understand the fact that pi rho 1 plus pi rho 2 must be equal to 1. Now, if that's the case, then I can refer to pi rho 1 as pi, and I can refer to pi rho 2 as 1 minus pi. So I really just have one parameter, which is why sometimes people, instead of writing it this complicated way, write it in this much simpler way in the case that you have two outcomes. Now, when you don't have two outcomes, then sort of all the bets are off the table, and you typically would rewrite it in the following way. Now, let's go back for 1 second and sort of jump ahead a little bit to, sort of thinking about computational efficiency, which will be sort of an important point in this class. Let's go back and think about my random variable written as the sum pi rho sub m delta function rho sub m of r. This form as written is actually typically quite complicated to deal with because it involves a sum. Whenever we have sums, and certain terms in the sum are extremely small, they can suffer from, sort of precision error and being sort of ignored. And we typically want to avoid sort of any kind of round-off errors. So it's always nice to have things written as products and not things sort of written as sums. So there's another representation for the probability density for a discrete random variable, which is less intuitive, doesn't appear sort of as a sum of spikes with their associated weights, but instead it's written as a product form. And it's this product form that we will almost universally use in computation later on in class. So how is this product form written? Well, sometimes we write it out as follows. I'm going to write it and then tell you what each one of the symbols are. This is pi to the rho 1 raised to the delta rho 1 of r all the way to pi rho m delta rho 1 rho m, of r, which I can rewrite as the product. The symbol here is a product. There's a line underneath. M from 1 all the way to big M, pi rho sub m raised to the delta rho sub m of r. So there's a new symbol that popped up here, and it's this delta. This delta has a name. I should write it out fully. And it's called a Kronecker. Delta. And the Kronecker delta is equal to 0 when rho 1 is not equal to r, and it is otherwise equal to 1. So let's make sure that this product form here makes sense to us. Suppose again that I have two outcomes, heads or tails. So my rho 1 coincides with heads and my rho 2 coincides with tails. If my r, my random variable, is realized to heads, then r is equal to rho 1. And what I find is that this delta, therefore, is equal to 0. If that delta is equal to 0, then pi raised to the 0 is simply 1. So I find that my p of r is proportional to pi of rho 1, which makes perfect sense. My probability of heads, because my r was realized to heads, is proportional to the probability of heads raised to the 1th power, the 1. So maybe writing this out a little bit more explicitly, if r is heads, and therefore r is realized to the first outcome, which is rho 1, and my p of r I said was this, p of rho 2, delta rho 2 of r, then delta rho 1 of r I know is equal to 1 because I just said r was realized to rho 1. Similarly, delta rho 2 of r is 0 because r was not realized to rho 2. Therefore, what all this means is that p of r is proportional to, well, pi rho 1 raised to the 1 times pi rho 2 raised to the 0, which is none other than pi rho 1. Makes sense. So the one challenge again is that, this formulation here may be a little bit less intuitive than thinking of discrete probability densities as a bunch of spikes reweighted by weights. But on the other hand, what we find is the results that we anticipate, and this form of probability densities written as products is much easier to deal with. One thing that's going to become clear is that if we oftentimes we deal with log probabilities because probabilities can be very small numbers. So when we deal with the log of this probability, this will become log of the sum of each one of these pi's. So log pi rho 1 plus log pi rho 2 plus log pi rho 3 and so forth. Even if pi rho 1, pi rho 2, pi rho 3 are extremely small, their log will not be that small, and therefore we will mitigate round-off errors and other kinds of numerical underflow.